Okay, ladies, we are going to go over nuclear reactions. We're going to go over 5 types. And yesterday we talked about 3 of them, so I'm going to review those 3, okay? Now, remember, the idea in a nuclear reaction is it's actually easier than balancing chemical reactions because all you have to really worry about is 2 things. One is make sure that the mass is the same on both sides of the equation, and make sure that the nuclear charge is the same on both sides of the equation. So what I mean by that is, so here's an example of something called alpha decay. So in alpha decay, what happens? What do you lose? Yeah, basically you're losing a helium atom, right? Now how do you balance these equations? Well, on the left side you see the symbol of your atom, right? And it's got the mass number and the atomic number. And this is the mass number up here. And then this is the atomic number. Now if you look on the right, so actually let's look at this equation. So the mass number is 238. On the right, it's 234 and 4, which add up to 238. So that's balanced. If you look at the nuclear charge, on the bottom, you see 92 protons. That would be, what would the charge be? It would be 92 plus, right? On the right, what do you see? 90 protons and another 2 protons. So when you're balancing nuclear reactions, make sure the mass is the same on both sides. Now, truthfully, the mass is not going to be the same, but it's so slightly different that you won't even notice it. So we can ignore it for now. All right? So this is an example. This is alpha decay. This is what Rutherford used in his gold-foil experiment to study the nature of matter. We talked about yesterday that smoke detectors use americium. They undergo alpha decay. Okay? That's the first type of nuclear reaction. The second type of, before I talk about the second one, we're going to review this really quickly, okay? What is this? Standard model. This explains matter in the universe. It's missing the Higgs particle. And these are what make up matter. You notice that protons and neutrons are not there because they're not fundamental particles. They're made up of quarks, up and down quarks. And on the right, in the red, you see the particles that explain how force works. Or these are the particles that are exchanged when we experience force. Like, for example, when you experience magnets that repel each other, it's actually the photon that is carrying out that force. When you talk about what holds the nucleus together, that's the gluon that holds the nucleus together. Because otherwise, think about protons. Nucleus has all these protons, and what are they going to want to do? They're going to want to... Protons are what charge? Yeah, what are they going to want to do? They're going to want to repel. So obviously there's the gluon that holds it together, right? And then on the bottom right, we have the weak force. That's actually the force that changes the atom into a different atom. So in this example here, the weak force would change carbon into what? Into nitrogen. Now this is the beta minus decay. In this process, what we're releasing is this thing called an electron, and that's actually a fundamental particle, which we can see right here. Here's your electron. And this other particle that is called the electron antineutrino, which looks like this. Now, this symbol, V with a little e, you can see it's right here. It's circled, the electron neutrino. You can see it right here. These 2 particles, in the electron and the electron antineutrino, they're not massless, but they're so light that we can consider them massless. Okay? If you look here, there's the mass of the particle. Okay, so photons, light, have no mass. These 2 are considered to have very little mass. So very, very little mass. We're going to ignore them. Let's say they're massless, although they're not really massless. So the electron neutrino is V little e. The electron antineutrino is its antimatter counterpart. So remember yesterday we talked about matter and antimatter. So when the universe was first created, you had matter, but then you had antimatter. So like there's the electron, and then the antimatter equivalent is something called the positron, right? Which is the same as the electron, but it's positively charged. And when they meet, they actually annihilate each other, right? So the electron antineutrino is just the antimatter partner of the electron neutrino. So this is beta minus decay. So if you think about balancing out the equation, right? What do you see on the left side? You have the mass, which is what? 14. And on the right side, what do you see? 14. Because we're going to consider these two as basically no mass. So we're actually going to lie a little bit just to make our life a little easier, okay?
Oh, yeah, there, okay. Thank you very much. How about we begin?
Now on the bottom left corner, you'll see the nuclear charge. So on the left side, you see 6 protons. So that would give you a charge of plus 6. On the right side, what do you see? You see 7 protons, which gives you a charge of plus 7, but also a charge of minus 1. And what does plus 7 minus 1 add up to? Plus 6. So now the charge is the same on both sides. All right? So balancing out the nuclear reactions, you got to make sure the mass is the same and the nuclear charge is the same.
Where's the minus 1?
Right here. So take a look. So see the electron?
Oh, okay.
See the minus symbol? So it's losing a negative charge.
But then is it also overlapping?
That's not a negative sign. That's placed over the VE to signify that it's the antimatter component or partner of the electron neutrino. That's not a negative sign. Although it looks like a negative sign, doesn't it?
So it gains the proton, but then it also loses the electron.
Yes. Yes, it does. To keep the charge the same. Now, the beta positive decay is the opposite. So if you look in a beta minus decay, the nuclear charge goes up by 1. So what we're doing is we're actually converting a neutron into a, remember what we talked about yesterday? A neutron gets converted into a proton. So in a beta minus decay, the neutron actually gets converted to a proton. In a beta positive decay, it's the opposite. So if you take a look, the mass number is 23, so that's the same on both sides. But look at the nuclear charge. It's 12, and now it's 11 because we release something called a positron. Okay? So what happens in the beta positive decay is a proton gets changed into a neutron. So the weak force changes the nature of either a neutron or a proton. So we talked about the example. Here's, for example, PET scanner uses positrons. When they get released, they collide with electrons, they annihilate each other, and they release energy. And you can track that and do like medical imaging with this stuff. So if you think about what's happening, right? What's happening in beta decays? In a beta minus decay, a neutron gets changed into a proton. Now, remember, protons and neutrons are made up of quarks. A proton is how many up quarks? 2, and 1 down quark. And a neutron is the opposite. It's 2 down quarks and 1 up quark. So if you think about what the weak force does, is it changes a neutron into a proton by converting a down quark into an up quark. Well, so remember, a proton is up, up, down, or down, up, up. A neutron is the opposite. It's down, down, up. So if we change a neutron into a proton, you'll notice one of the down quarks has to be changed to an up quark. So that's what happens in a beta minus decay. So what would you predict happens in a beta positive decay then? Yeah, it's the opposite. So a proton is converted into a neutron by changing an up quark into a down quark. So we go from DUU to DDU. So that's actually what's happening at the level of the nucleus. Okay, sorry? Yes, it does. This process does happen naturally. Now, can be done artificially, right? If you think about what we talk about later on, like a nuclear bomb, that's artificially controlled, right?
But I thought all nuclear reactions release energy.
They do. But you asked me, like.
No, I'm not asking another one. So how they
a lot of these nuclear reactions don't. They're just natural. They just happen all the time. So you don't control them. Yeah. And you mentioned the release of energy. So these reactions do release energy. And depending on the type of reaction, sometimes you release a lot of energy. So remember we talked about like you can release X-rays, but you can release even more energetic rays called gamma rays, which we talked about yesterday. So these are things that we're not going to include in our equations when we're balancing them out, but I want you to be aware that these nuclear reactions, which can release a lot of energy, can release things like gamma rays, which are very, very powerful. So let's look at an example of the three types then. So here is the uranium decay by alpha emission, the rubidium-87 decayed by beta minus. So your book uses beta minus. This is the symbol for beta minus in your book, but we're actually going to draw out what the beta minus and the beta positive actually looks like, okay? So C is an example of beta positive or positron emission. And then yesterday we looked at the solutions. So let's see if you remember. The first one is an alpha decay. So that one's done for you. Second one is, well, just by looking at it, what happens to the nuclear charge? Goes up. So what must have been released in this case? Yeah. So if you think about the math, here's 37, here's 38. These two have to be the same. So this has to be a negative on this side, because -1 and plus 38 is plus 37. And then we release an anti-neutrino. And I know you're right. Who mentioned this? This, as Anissa, it does look like a negative sign, but it's not. It's not a negative sign, okay? So this is a particle that gets released in this decay process.
Oh, but it doesn't change the charge.
No, it's neutral. If you look at the charge, so the first row is the mass. So the first thing that you see is the mass. The second thing that you see is the charge. So the up quark is plus 2/3. The down quark is minus 1/3. The electron is -1. The electron neutrino is 0. It has no charge at all. Okay, so there's no charge there. Yep.
But didn't you say that using the law of conservation of matter?
Yeah.
Didn't you say that nuclear reactions are exceptions to that? Because atoms are
Yeah, so what I said was that we're going to assume that the mass is the same on both sides, but it's actually not.
Okay.
There is a slight drop in mass. Can I come back to that?
Yeah.
Okay, I'm going to come back to that. Because you're right, the mass is not exactly the same on both sides. So then the last one is an example of not beta minus, but beta positive. So because we can see that this is plus 19, this is plus 18, so we're missing a plus 1. So we release a positron and an electron neutrino. Okay? All right. Now, So yesterday we talked about those three reactions. Today I'm going to introduce two more, which are really, really important. One of them is nuclear fusion, which is what makes the sun shine. And this is a process where atoms actually come together to form a bigger atom. So in this picture here, you actually see in the bottom left corner, you see three different types of hydrogen. Okay? So you see, sorry, you only see two different types of hydrogen. I apologize. You see deuterium and tritium. Now, when you think about hydrogen, you think of something that has a mass of 1. So that means it has 1 proton and how many neutrons then? Remember the mass number is the number of protons and neutrons, right? Yeah, so H1, 1, so like what you're seeing over here, would have 1 proton and 0 neutrons. So its mass would be 1 because it has 1 proton. But deuterium actually has, if you can see in this picture, it has 1 proton and 1 neutron. So this would be an isotope of hydrogen. And tritium has 1 proton with 2 neutrons. So it have a mass number of 3. Okay? So there's three different types of hydrogen then. There's H1, there's H2, and there's H3. Okay? Now, in the equation here, up here, you're seeing an example of fusion where 4 H1 atoms come together to make, what are they making? Helium. So this is what happens in the sun. The sun has, most of the fuel in the sun is hydrogen, and it converts it into helium. And when it does that, it releases energy. And we'll talk about that a little bit. I'm going to get back to this, what you were saying about the mass, okay? But let's just look at balancing this equation up for a second. Now, H1 is how many protons? 1 proton. If I have 4 of them, then that's 4 protons, right? But how many protons does helium have? 2. Okay, that means that 2 of the protons were converted into 2 neutrons. Because if you're thinking about helium, helium-4 has 2 protons and 2 neutrons. So that means 2 protons were converted into neutrons. So what's the process that explains the conversion of protons into neutrons? Is that beta minus or beta positive? It's beta positive, right? And that's what you're seeing right here. Okay. Normally, when we write the beta particle, we just write it with plus or minus. You see this here. This refers to its mass on top and its charge on the bottom. So you don't need to write the 0 and 1. Okay, we could ignore that. And the other thing is normally when we write the electron neutrino, there's a little e there at the bottom, which is not, for some reason it's not here. Let's just pause this for a second. Alright, sorry. There was an interruption there. But if you look at the nuclear fusion reaction, you can see it's balanced, right? You can see that the mass is, on the left is 4 times 1, which is 4. On the right it's 4. Because remember, these two particles are considered to be massless. Although in ISA, they're not really massless, right? And you can see that the nuclear charge on the left side is, well, 4 protons would be 4 plus 4. On the right side, 2 protons is plus 2, but then we have 2 beta positive particles, so that's plus 2 and plus 2 is plus 4. So the left and the right side are balanced.
So why do they call this nuclear fusion? Oh, I get it! Wow, that's so cool.
Because in nuclear fusion, what you're doing is you're making a bigger atom. The word fusion means to put things together, right? And you can see in this picture that this molecule over here, which is an atom, is bigger than the molecules that we start with, which is deuterium and tritium. Yes?
So the 2 protons of helium combined with the 2 electrons
No.
The one with the electron positron.
Yeah, it's positron, yeah?
Oh, that's the positron. That combines with the two protons in ion places equal 4.
Right. If you think of it, if you think about balancing the charge, you have 2 protons and 2 beta positive particles. So +2 and +2 is +4.
And hydrogen has 4 protons.
Right. So on the left side you have +4, and on the right side you have +4. If you think about, now I want you to think of this for a second. This is what the sun does. Right? The sun takes hydrogen and smashes it into helium. Smashes them together to make helium. But I want you to think about something for a second, because when you really start to think about problems, you're like, oh, wait, how does that happen? Because you learn in grade 9 that things that have the same charge don't like each other. So my question to you is, how do you get protons and put them together to make something bigger? Because I was taught in elementary school that if 2 things have the same charge, they will never come together. Right? So the force that explains attraction and repulsion is the electromagnetic force. So how do you overcome that? I'm not going to answer that question yet. That's not gravity. I'm not going to answer that question yet. Can we look at fission for a second? So fission is the exact opposite. In fission, you take a big atom. So in fusion, you usually take small atoms, you put them together and make bigger atoms. In fission, it's the other way around. You take a big atom and you break it up. So in this case, the big atom is uranium. Uranium is quite large. It's got a mass of 235. Now, how do you break it up? Well, in this case, you strike it with what do you think that is, this particle on the left side? What do you think this is? N. So think N. It has a mass of 1 and it has no nuclear charge, so this is a neutron. So you take a uranium, you smash it with a neutron, and what happens is it breaks up into smaller atoms. But again, is it balanced? Okay, well, take a look. On the left side, what's the mass? Well, it's 1 and 235, so that would be 236, right? So on the left, we have 236. On the right, you have barium, which is 141. You have krypton, which is 92. That adds up to 233, but we have 3 neutrons. Each has a mass of 1. So that adds up to 236 now. If you think of the nuclear charge, on the left we have 92. On the right we have 56 and 36, which also adds up to 92. Now, in a nuclear fission, you have the opposite problem. Why doesn't an atom break up? Right, because the gluons hold them together. There's a strong nuclear force that holds them together. So, if you think about fusion, the question was, how do you get things that are the same charge to come together? That doesn't sound like it's possible. In fission, it's the opposite problem. How do you break up a nucleus when the strong force holds it together?
Is the strong force?
It's carried by the gluon. So here's the model. No, the neutron. Here's the model. This is a picture that describes what happens in fission. Here's your atom. The atom gets struck by a neutron and it stretches in size, so it becomes an oval. And then the oval pinches in like a peanut. And then, and that's actually why it's called binary fission, because when it was described, it's binary fission, which is mitosis, but in bacteria. It's not mitosis, but it's like mitosis in bacteria, right? The idea with the strong force works over a very, 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 very short distance. So when you take the nucleus and you stretch it out, now the strong force no longer can exert its effect because the nucleus is too stretched out. Whereas the electromagnetic force is the opposite. It works over a long distance. So if we go back to this problem, it's like, okay, how do you get two charged particles close enough to overcome that electromagnetic force? Here it's, how do you get things far enough to overcome the strong force? It's the exact opposite problem. The answer is really ridiculous. You'll never have to explain this on a test. If I tell you, you're probably not going to believe it. And I'm going to have to even use the word magic in the explanation.
I already don't believe you.
Do you remember the answer of why electrons don't produce every color when they get excited? The answer was quantum jumping, right? Which means that they start off at one level, right? They can be here. So then maybe they're here, and they can go to this level, and then they don't cross this space, right? So think about that for a second. They pop into and out of existence, right? There's no other explanation. There's no other explanation.
They still exist.
No, but if they don't touch anything.
But you can't go from point A to point B without crossing that space unless you pop into and out of existence. So the answer to this question, which is, how do you explain how these things can come together or break up, is a process called quantum tunneling. Okay?
I thought I was going to.
So the idea of the idea of quantum tunneling is that think of a hill, right? Think of a hill. Think of it this way.
Okay, like black holes, like wormholes that like the paper goes like this and then goes.
Well, yeah. So okay, sure. The idea is, imagine that if I want to bring two protons together, I know that's not going to happen because they're both positively charged. They're gonna, as soon as they get close to each other, they're going to start repelling, right? So how am I going to get them together? So the analogy is like top over there, like a person climbing a hill that's so high that it would be impossible to get over the hill, unless there's a tunnel. Unless you can magically, because imagine the challenge was get to the other side of the hill. Imagine there's a tunnel. So you can pop into and out of existence. Just like electrons can jump from one point to another, things can move from one location to another. So it's possible that protons could pop into existence and be close enough that they get captured by the strong force. Or it's possible that they can pop into existence in a different location where they're far enough that they can be split. Magic! Never have to explain this. You could erase it. I thought that was kind of cool to
Sir,
explain.
if you can explain quantum tunneling in one sentence, do it.
Magically pop into and out of existence. How's that?
Does it work like
What's that? I don't know if it's the same thing. Yeah. Yeah. So, Anissa, can I answer your question about the mass?
Yeah.
So the mass is not the same on both sides of the equation. There is, in these conversions, there is a little bit of mass lost because a proton and neutron don't exactly weigh the same. You don't have to calculate this. You'll do this in grade 12 physics, but not in grade 11. So there is a little bit of mass that is lost. For your balancing of nuclear reactions, don't worry about it.
Yeah.
But that little bit of mass actually translates into a heck of a lot of energy. If you think about the bomb that was dropped on Hiroshima and Nagasaki, the amount of energy released from very little mass was enough to level Hiroshima and Nagasaki. Because the equation that explains how much energy is released is this one right here. It's E equals mc squared.
So what's C?
C is the speed of light. And C is 3 times 10 to the 8. So when you square 3 times 10 to the 8, you get a huge number. 9 times 10 to the 16. What does that mean? Right now, for you, probably nothing. To be honest with you, unless you work it out. But that means that the amount of energy that fission and fusion release is millions of times more than like combustion. If you think about like a gas can that explodes, a nuclear bomb would be millions of times as powerful. So let's look at some examples of, what's this? Fission or fusion?
I don't know. Wait, what's vision?
No, this is
Vision. Oh.
This is fission. Because you have a large nucleus that splits into a smaller one. 92 into 52. So what are we missing then? Well, by the way, this one is already done for you. This is the first example that we looked at. So what are we missing? Well, we got 236. So our mass number is 236 in total. On the right, we have 137 and 2 neutrons, which is 139. So what are we missing? 97. So we're missing 97 in terms of mass. We are missing 42 and 52. We're missing 40 in terms of nuclear charge. So what's the 40th element in your periodic table? Yep. So you look, the 40th element is zirconium. That's it.
Why is it easier than chemical?
Because we're doing it together. Look at the next one.
Yeah, that's true.
Uranium. Again,
Iron arm.
235 and 1 adds up to 236. By the way, all these examples are with uranium. It doesn't have to be uranium. Okay? So on the right, you have 137 and 3 neutrons, which adds up to 140. So we're missing 96. Because 96 plus 140 is 236. We have 92 and 55. We're missing 37. So, yeah, so 37 would be rubidium.
Wow.
Alright? The last one we have 235 and 1 is 236. Again, still 236. They're not always 236. Now we have 94 and 140. That adds up to 234. So what are we missing? We're missing 2 neutrons.
So you don't,
In this case, the nuclear charge already taken care of, right? 38 and 54 add up to 92. That's nuclear fission. Nuclear fusion.
Wait, so you just need to pause for a second?
I'm recording this so you can watch this. So here we have 2 hydrogen atoms, 2 H1s coming together to form H2. But take a look at something. What's the nuclear charge? 1 and 1, which is plus 2. On this side, it's only plus 1. So so we're missing something that is positive then. That has to be the positron. And therefore also the electron neutrino.
Do it always come with the electron neutrino?
Yes, at least I'm pretty sure it does. So the second one is, we can see its mass is 3. So this is 2, so this must be 1. And the nuclear charge is 2, so this is 1, then this must be 1. You know how easy it is? You learn counting in elementary school.
I know, when we go home, I'm like, oh, this is so easy. I go home.
Now what about this one? 3 and 3 is plus 6. Here I see plus 2, so this must be, I'm sorry, not plus, that's the mass number. So it has to be a mass of 4. The nuclear charge is plus 4. And this is plus 2. So this has to be 2. Right? The nuclear charge is 2 and 2, which is plus 4. And on the right side, it must be plus 4 also. So I need 2 and 2. And this one is 3 and 1 give me 4, so that's fine. 2 and 1 should be 3, should be plus 3. But I always see plus 2. So I'm missing a +1. Positron again. So this is the VE is the electron neutrino. The VE with the line on top is the electron antineutrino, which comes with the electron. And then this one is combined. So what I'm going to do is I'm going to leave this last one for you guys to do. I'm going to pause the video. I'm going to put the answers in. And then you can check at the end of the video for the answers, all right?
Okay.
Actually, I'm going to do them right now. If you guys want to grab your books, you can go ahead and grab them.
Can you give me one? Pat, can you get me those two brothers? We can do this.
I do. Why is it white?
Come on. No, but everyone crossed my face up.
All right, those are the solutions.
Hi. Yeah.